Hello everyone and welcome to the video lesson for Chapter 10. In this first section I'm going to introduce the notion of scalable databases, focusing on scaling relational databases. In the early 2000s, the world of databases was a comparatively calm and straightforward place. There were a few exceptions, but the vast majority of applications were built on relational database technologies. Systems leveraged one of a handful of relational databases from major vendors, and these still dominate the top 10 market share, as you can see on the next slide. If you could jump into a time machine and look at similar rankings from 2001, you'd probably find 7 of the top 10 current databases, all relational, in similar places to the ones they occupy in 2022. But if you examine the top 20 in 2022, at least 10 of the current database engines did not even exist 20 years ago, and most of these are not relational. The market has enlarged and diversified. The data systems we build today dwarf those of 20 years ago, when relational databases ruled the earth. The growth in dataset size and complexity has been driven by internet-scale applications. These create and manage vast quantities of heterogeneous data for literally tens of millions of users. This includes, for example, user profiles, user preferences, behavioral data, images and videos, sales data, advertising, sensor reading, monitoring data, and much, much more. Many datasets are simply far too big to fit on a single machine. This has necessitated the evolution of database engines to manage massive collections of distributed data. New generations of relational and non-relational database platforms have emerged with a wide range of competing capabilities aimed at satisfying different use cases and scalability requirements. Simultaneously, the development of low-cost, powerful hardware has made it possible to cost-effectively distribute data across literally hundreds or even thousands of nodes and disks. This enhances both scalability and, by replicating data, availability. Another major driver of database engine innovation has been the changing nature of the application requirements that populate the internet today. The inherent strengths of relational databases, namely transactions and consistency, come at a performance cost that's not always justified in sites like Twitter and Facebook. These simply don't have requirements for every user to always see the same version of, for example, my tweets or timeline updates. Who cares if the latest photo of my delicious dinner is seen immediately by some of my followers and friends, while others have to wait a few seconds to admire the artful dish that I'm consuming? With tens of thousands to millions of users, it's possible to relax the various data constraints that relational databases support and attain enhanced performance and scalability. This enables the creation of new, non-relational data models and natively distributed database engines designed to support the variety of use cases for today's applications. There are trade-offs, of course. These manifest themselves in the range of features a database supports and the complexity of its programming model. Databases that support the relational model and the SQL query language represent some of the most mature, stable, and powerful software platforms that exist today. You'll find relational databases lurking behind systems in every type of application domain you can imagine. They're incredibly powerful, complex, and amazingly successful technologies. Relational database technology was in fact designed and matured when datasets were relatively small by today's standards, and the database could run on a single machine. As datasets have grown, approaches to scale databases have emerged, and I'll briefly cover some of these in the following slides. Relational databases were designed to run on a single machine, which enables shared memory and disks to be exploited to store data and process queries. This makes it possible for database engines to be customized to run on machines with multiple CPUs, disks, and very large shared memories. Database engines can exploit these resources to execute many thousands of queries in parallel and provide extremely high throughput. The picture on the slide here depicts this scale-up scenario. The database is migrated to new, more powerful, probably virtual hardware. While there is database administration magic to perform, the migration and to tune the database configuration to effectively exploit the new resources, the application code should require no changes. There are three main downsides to scaling up. They're listed on the slide here. The first is cost. Hardware costs tend to grow exponentially as the computational resources offered grow. Also, you may have licensing costs that also grow as you deploy more database engines. For availability, you still have a single database node, albeit a really powerful one. If it becomes unavailable, your system is down. A multitude of high availability HA solutions exist that offer mechanisms to detect unavailability and fail over to a backup copy of the database. Many HA solutions are database dependent. You also still have to worry about growth. If your database continues to grow, another migration to more powerful hardware is kind of inevitable. Scaling up is indeed attractive in many applications. Still, in high volume systems, there are two common scenarios in which scaling up becomes problematic. First, the database grows to exceed the processing capability of a single node. Second, low latency database accesses are required to service clients spread around the globe. Traversing intercontinental networks and the additional latency just doesn't cut it. A common first step to increasing a database's processing capacity is to scale out using read replicas, as depicted on the slide here. You configure one or more nodes as read replicas of the main database. The main database node is known as the primary, and read replicas are known as secondaries. The secondaries maintain a copy of the main database. Writes are only possible to the primary, and all changes are then asynchronously replicated to secondaries. Secondaries may be physically located in different data centers or different continents to support global clients. This approach enhances scalability by directing all reads to the read replicas. It is hence highly effective for applications that must support read-heavy workloads. Reads can be scaled by adding more secondaries, reducing the load on the primary. This enables it to more efficiently handle write requests. In addition, if the primary becomes unavailable due to a transient failure, read requests directed to secondaries are not interrupted. As there is a delay between when data is written to the primary and then successfully replicated to secondaries, there's a chance that clients may read stale, out-of-date data from secondaries. Applications must therefore be aware of this possibility. In normal operations, the time between updating the primary and the secondary should be small, for example, a few milliseconds. The smaller this time window, then the less chance there is of a stale read. Read, replication, and primary-secondary based database architectures are topics I'll return to in much more depth in following video lessons. Splitting up or partitioning data in a relational database is a technique for distributing the data over multiple independent disk partitions and database engines. Precisely how partitioning is supported in a product is highly product and vendor specific. In general, there are two strategies: horizontal partitioning and vertical partitioning. Horizontal partitioning, as shown on the slide here, splits a logical table into multiple physical partitions. Individual rows are allocated to a partition based on some partitioning strategy. Common partitioning strategies are to allocate rows to partitions based on some value in a row, or to use a hash function on the primary key. As shown on the slide, you can allocate a row to a partition based on the value of the region field in each row. Vertical partitioning, also known as row splitting, partitions a table by the columns in a row. Like normalization, vertical partitioning splits a row into one or more parts, but for the reasons of physical rather than conceptual optimization. A common strategy is to partition a row between static read-only data and dynamic data. The example on the slide here shows a simple vertical partitioning for an inventory system that employs this scheme. Regardless, the very nature of relational schemas with data split across multiple tables makes it problematic to devise a general partitioning strategy for distribution. Horizontal partitions of data ideally distribute tables across multiple nodes. However, if a single request needs to access data from multiple nodes or join data from distributed partitioned tables, a high level of network traffic and request coordination is required. This may not give the performance benefits you expect, and I explore these in a sidebar in Chapter 10 in the book. This section from the Google Spanner documentation, Spanner is a distributed SQL database offered on Google's cloud, emphasizes that point. It simply states join operations can be expensive. This is because joins can significantly increase the number of rows your query needs to scan, which results in slower queries. Hence, you need to be very cognizant about your use of joins and the data models that you deploy on a distributed SQL database. Nothing comes for free. Many vendors have made efforts to scale their relational databases highly successfully, and some of the examples are listed on the slide here. I haven't got time to go into exactly how these databases work in this video lesson, but some of the information, for example, on Oracle LAC is described briefly in my book chapter. That's it for this video lesson for the first part of Chapter 10. Thanks for listening. Next, I'm going to talk about NoSQL databases, which have emerged as competitors to the relational database world over the last decade or so.